So formation of diazonium salts. So here's our alkylamine, and here's sodium nitrite and HCl, and that makes nitrous acid, but we don't keep nitrous acid in the lab. It's very reactive, and that's the whole point of it here. So we form it in the reaction flask, and it makes this triple bonded thing, and the chloride. So here's our diazonium salt. Now this thing's kind of unstable because it can react and kick out N2 gas. Primary amines react with nitrous acid to form a diazonium salts. The diazonium salts are unstable and decompose into carbocations and nitrogen. So why would we mess around with that? So one reason why you don't want to eat a lot of lunch meat is sodium nitrite is put in meat, and you get nitrous amines, which react with DNA, carcinogen. The amine attacks the nitronium ion and turns into an N-nitrosamine. A proton transfer, you've seen this word before, tautomerism, form nitrogen to oxygen, forms a hydroxyl group and a second nitrogen bond. Protonation of the hydroxy group followed by the loss of water gives the diazonium ion. And that's all we care about. We don't really care a whole lot about this mechanism. And this is useful for arenediazonium salts. So every time I get to chapter 16 and 17, I'm always like, where's this chemistry? Well, you don't get it till you get to the amine chapter. But here's toluene, orthopara-director. So here's our nitration reagent. Put the nitro group in the para position. And here, iron and HCl, followed by some base, reduces the nitro group into an aniline group. And here is our sodium nitrite and HCl. We don't care about that mechanism. Here is our diazonium salt. By forming and diazotizing an amine, an activated aromatic position can be converted into a wide variety of functional groups. This thing falls apart easy. We imagine, from what we just saw, this falls off and puts a carbocation there. And so it doesn't matter really what happens. Various reagents, we can put a new group on there. So here we've turned an aniline group on a benzene ring into this diazonium salt. And this is how phenol is commercially made. They nitrate benzene, they reduce it to aniline, they hit it with sodium nitrite, with HCl. They form this salt, and then they just put it into they add warm acidic water, and voila, there comes phenol. And here's some cuprous compounds, cuprous chloride, cuprous bromide, and that would be copper 1 cyanide, copper 1 bromide, copper 2. And so that's how you can put a cyanide group on a ring. And fluorinations, F2 gas is explosive to work with, it's uncontrollable, it's not selective, but this is how you put a fluorine on a benzene ring. Nitrate benzene, hit it with sodium nitrite and HCl, you form your diazonium salt, hit it with HBF4. All right, here you can hit it with Ki, and hypophosphorus acid just puts a hydrogen back on. And you might be, why would you want to do something like that? Well, you could probably put say you had something like toluene, you could nitrate it, and then with those directors, or you could nitrate something in a position, put some other substituents on, then take it away and get rid of it. Deamination and azo dyes. So here you're reacting it with another benzene ring. Or AR could just be any aromatic compound like naphthalene. So the Sandmeyer reaction, those were those copper reagents. So like cuprous chloride, cuprous bromide, or cuprous cyanide. Here's our aniline group, sodium nitrate, sodium nitrite, HCl, makes that diazonium salt, hit it with cuprous chloride, puts the chloride there. Here you see the same thing, putting a bromine on the ring. So a tiny review from the ketone chapter. We had a bunch of nitrogen containing compounds that would go right to where the oxygen is. So we had the amines, and a oxime was when there was a hydroxide there. So what's the organic chemistry definition of reduction? Decreasing oxygen content or increasing hydrogen content. And you can see we got rid of that oxygen for sure and added a hydrogen here. So a ketone or aldehyde can be converted into a primary amine, and this is called a condensation. So hydroxylamine, 0 alkyl groups with a ketone or aldehyde followed by reduction of the oxime. Here's the oxime. And to reduce this, here's our lithium aluminum hydride. If I put a 4 here, that's just sodium borohydride, and that's a similar reagent. So here is a primary amine, ketone or aldehyde. So here's our amine formation. Looks like that quiz question. And we reduce that and we can get a secondary amine. And in the ketone chapter, we call this thing a Schiff base. An N-substituted amine is a Schiff base. You reduce that, you get a secondary amine. And you see this is kind of general. We did an oxime. You probably do about the same thing with just ammonia. Then we did an alky amine. Here's a dialkylamine. So here is a tertiary amine. And of course we end up with nitrogen with 4 bonds. And you do it in the same flask and just add the second reagent. You don't isolate it. So with all that under your belt, I'm going to do what's known as retrosynthetic analysis. Here's the product I want, and I'm going to ask myself, what can I imagine this coming from? So earlier we saw if we reduce this, a nitrile can be reduced to a primary amine. So now how could we get to that? Well, we just went over this diazonium salt business. And so here we'd want our cupric cyanide. So here we'd want our sodium nitrite with our HCl. All right, now that we got all that figured out, see how we did. Sodium nitrite and HCl, cuprous cyanide, lithium aluminum hydride, or catalytic hydrogenation. Difficulty of 3. I haven't seen any 4s. They go through 1 through 3. All right, that should help you quite a bit with your take-home quiz. That will be all for today.